Hello geometers and general seekers of truth. In this video we will look at an application of the triangle inequality theorem that uses an example with some fencing. So let's say we are building a triangular playground with 3 sides, and 2 of the sides we know is 100 feet and 200 feet, and we want to know if going out and buying 580 feet of fencing is enough. Well, we know we need at least 300, so we're going to have a side here that's 100, and we're going to have another side that's 200. So let's say we had a side that was like this, 200, right? Well, how big is this side going to have to be, right? Now, what we also don't know is what this angle is going to be. We don't know if it's going to be very wide or if it's going to be very, very narrow. So what if, the fencing is like this? You have like something this is 100 and this is 200, right? So clearly in this case, the additional line of fencing, this would be smaller than this side length here. So this blue side here would certainly be smaller than, this blue side here would certainly be smaller than this yellow side here. So we want to make sure that we buy enough fencing, but we don't want to buy too much of it. Okay? So what we can think about this is that we have a triangle, and we want to know how big this side can get. Okay? Well, let's assume that x is huge. Let's assume that we widen the triangle to be very big. So like this length here is about 100, and like this length here is 200. And I mean, how wide could we possibly make this third side, right? So how wide could this really be? Right? So I'm using x in both cases to illustrate that there are lots of options in order to shape this triangle. We want the biggest size playground, of course. However, excuse me, we also want to be able to make sure that we accommodate for whatever streets and geographic considerations that there are. So to solve this, we can set up a inequality. We know that the smallest length, 100, plus the other length, 200, must be greater than, definitely must be greater than x. Okay? So x here would have to be some number that is, x can't be too big. So x can't be like 1,000,000. So if the other side length here is like really, really large, then there's no way that we can make a triangular playground. So these two values here, 100 and 200, is the values that are putting a restriction on x. So we know that x must be no more than 300. So that means the total fencing is no more than 100 plus 200 plus 300. Okay. So the total fencing must be less than 600. So actually 580 may not be enough. It could be enough, but it's not guaranteed to be enough, because if you open up the triangle here with 100 and 200 to be very wide, if this angle is very, very obtuse and very large, then you might not have enough fencing to cover all of it. So the answer here is no. Okay, so it could be enough, but we may need up to 600 feet of fencing. So there you have it, just a quick example of how to use the triangle inequality theorem in order to test and estimate some special cases. Now I'm going to continue and work on some examples that are a little bit more challenging. Okay, so in this example here, we know that measure of angle J is less than K, which is less than L, and we want to find all possible values of x. Well, clearly, if L is the largest angle, then this length here must be the largest length. So our inequality will set up as x plus 9 must be greater than, excuse me, not less than, must be greater than the other side, which is 21. So subtract 9 from both sides, so x must be greater than 12. And so that is our solution. Now, the other thing that I should mention, that this may not really be completely our solution, is we also have to consider for the fact that x must be smaller than 21, right? Because it can't be too big. If x is bigger than 21, then this statement here would no longer be true. We know that angle K is less than angle L, so we then know that 21 must be the largest side, so must be greater than x. So I should amend my solution just a little bit and say that x has to be greater than 12, but it can't be bigger than 21. Okay? So it's like the middle side of this particular triangle. Now let's look at this example where it's slightly more complex. Remember, we still know that J is the smallest, and that L is the largest, and that K must be somewhere in between. So we can compare the sides. If we look at the two smaller sides, so if J is the smallest, then KL is the smallest side. So KL plus the second smallest side would be JL. And that must be greater than the largest side, JK. No joking. Okay. So KL would be 20 minus x. JL would be 15. And that must be greater than JK. So JK is 12 plus x. Okay. So we got some solving to do. On the left side, we have 35 minus x is greater than 12 plus x. Add x to both sides, and we get 12 plus 2x. And that would mean this is gone. Right. And then finally subtract 12 from both sides, and we get that 27 must be greater than 2x. And that should divide one more time. 13.5 must be greater than x. Okay. But now remember what we had from last time. This isn't enough. X can't be anything. It can't be too big, right? Because if it was too big, let's say x was like 25. If x was 25, then this side length would be negative. Okay, so let's think about all of the restrictions on x. Let's look at here, right? If x was greater than 20, then this side length would be negative. So we also know that x must be less than 20. But we also have to consider another restriction on this, which is namely that we know that JK is the largest side. So we have to consider one more restriction in thinking about that JK has to be larger than KL, and we have to solve that variable as well. So 12 plus x has to be greater than 20 minus x. Add x to both sides and you get 2x. Subtract 12 from both sides and we get 8. And then divide by 2 and we get that x is greater than 4. So we have three restrictions. X must be less than 20. X must be less than 13.5. And x must be greater than 4. And we want to go with the most restrictive. Okay, so what would be the most restrictive out of all three of these? Okay. Well, if you want to visualize this it's easy to do this on the number line. Okay. So I'm going to put the three important numbers on here. X is 4, 13.5, and 20. Okay. So let's look at the restrictions. X must be less than 13.5. Okay. So anything bigger than 13.5 is out. So all of this stuff here is out. Okay. X must be less than 20. So anything bigger than 20 is out, but we don't have to worry about that because anything bigger than 20 is also bigger than 13.5. And then finally, X must be greater than 4. So anything that is less than 4 is also out. So all of this region here is not possible. So I'm crossing this off. Okay. So what are we left with? Well, we're left with just the region between 4 and 13.5. So we can write that down as our final answer, that X must be some number that's greater than 4. So all I'm doing is I'm flipping that around, and less than 13.5. Okay. And the point of this problem is that we have to check lots of different restrictions and then go with the most restrictive. Let's compare everything and then look at the most restrictive one, and those are the possible values of X. As always, ask for help if you need it. Keep working hard. Thank you for watching. Thank you for learning, and have a wonderful day.